For this problem, we're given h of s, and this is equal to 100 divided by s plus 125. We are going to create the straight line amplitude and phase Bode plot. We're asked what is the amplitude corner frequency and the value of a dB at 1 rad per second. We're going to go through all of this, but first we'll start out by converting this h of s to an h j omega. So we're going to have our h, we're going to have j omega, and this is equal to 100 divided by our j omega plus 125. I've also included some notes below the problem, and these can be found more in depth in the Google Docs linked below the like button. But we're going to continue on. We're not really going to use this second part, but we are going to use the first one right here, and we're going to use this to kind of set up our problem. And the bottom part is going to give us an idea of how we're going to look at the Bode plots. So we have this. Now we want to convert it to make it look something more like what we have to the left here. We're going to have our k, z1, p1 out front. Well, our z1 does not exist because remember, the z is for zeros on top and p is for poles, and this is in the denominator. So what we're going to have is our 100 out here. Our z is non-existent, so we're just going to have a 1 here. And this is over our p, which is 125. Next, we're going to have the rest of our stuff. We have this top part. However, for this top part, we're not going to put anything in, only a 1, because we don't have any zeros. So we're just going to have 1 divided by, we're going to have our j omega, we're going to have a 1 plus our j omega divided by our p1. And our p1 is 125. And so this is our equation. We can rewrite this as 100 over 125, and then out here we are going to have 1 over j omega, then we're going to have 1 plus j omega divided by 125, and then parentheses. So this is what we have now, and we are going to have to find a couple things for this. To start solving, what we can do is we can make a kind of chart for our Bode plot. And I'm only doing this because it's in OneNote. If we were to actually draw this out, it'd be a little bit, I guess, less linear, a little bit more realistic. But for our Bode plot, we're going to have super straight lines. And also, if we were to do this in like some kind of computer program like MATLAB, we would have more accurate lines. But we're just going to do this by hand. So if we look at this, we currently have 3 different parts. We have this part right here, we have this part right here, and then we have this part right here. Now I can't fit it in this page right now, but in the notes linked below the like button on page approximately 97, we have a whole chart of summary of Bode straight line magnitude and phase plots. We are concerned only with phase, and that's because it's asking us with the phase inflection right here. So that's why we're concerned with phase. So when we graph this, we're going to be looking at phase. So to start graphing this, we're going to look at our constant out front, the k, 100 over 125. If we look in the notes, again, linked below, but it's super important because we have these factor to phase already in there. So the factor to phase of our k right here is just going to be 0 degrees. So I'm going to make a 0 degree line along here. This is 0 degrees, and it's going to go all the way along here. Now, for our other ones, it's going to go to a certain point. When we draw a Bode diagram, normally it's, when we look at this way, our A and our omega, we have a 20 here, a 40 here, 60 here, and an 80 here. So we have all of these, and then right here we're going to have a 0.1, we'll have a 1, we'll have a 10, we'll have a 100, and then we'll have a 1000, and this will just keep going on and on. Next, we're going to graph our j omega, and when we write this, we can really write this as 1 over our j omega, and then we're going to have this in parentheses with an n. Now this n is going to tell us the slope. This is the dB, and this is what the a is. So this should really be a dB. And the n is for the slope. Now, for this problem, we have an exponent of 1, so we don't really have to worry about that. It's going to go down at a rate of 20, otherwise it would be steeper. So looking at this per the chart, we are going to have a flat line, so a 0 slope, but it's going to be at a negative 90 degrees. So it's going to be all along here. And it's important to know actually how far this graph is going. And that is what we're going to find out with this part. And this part is actually going to tell us what our WC is, and then we can find out what this is from there, and then fill in our Bode diagram to find out these. Now, to figure out this next part, what we're going to do is we're going to look at the notes. So we have 1 plus j omega, and then this is over 125, and then we have our n out here. Now, looking at the notes, since we have a p, remember this 125, what it really is it's a p. So I'm just going to rewrite that so it's a little bit easier to see. This is our p, and then when we look again at the notes, we can write this as p over 10, and this goes to p times 10. We know that the p here is 125, so we will have 125 over 10. This will give us 12.5, and this is going to go to 1250. So these are going to be the points that we go to, and looking at the notes, I guess I could just bring it over here really quickly. It looks something like this. We're going to be focusing on the lowest one right now, so it's going to be this one right here. We can see that it's going down from 0 degrees with a 45-degree slope to 90 degrees. This is a negative 90 degrees though, so that's important to note. And now we can draw this. So it starts at 12.5, and we'll just say that 12.5 is approximately right here. This is approximate 12.5, and this is going to 1,250, so we can approximate it to right here, 1250, and this is what we're going to look at. So looking in the notes, we can see that it starts at 0 degrees. So that means it's going to be along this line. And then from here, because we don't have an end, if we did have an end, it would be steeper. We are going to be going down here at a slope of 20. So remember, this is 20, and then this is like 40, somewhere around here. And this should line up with this 1,000. So at this 1,000, it should be 40. And since we're just drawing it by hand, it should be close, might not be 100% accurate. So from here, what we're going to do is after this, it's just going to flatten out. And then it's just going to flatten out for the rest of the time. So we have all of these different things right here. Now it's important to see where we have a change of our slope. And we're going to mark that down. So we have this here, and we have a change of a slope here. And the only change is because of our gray line. Before we do the first part, I'm going to do this last part down here. We'll see why in a second. So what are the 3 phase inflection frequencies? Well, we have 0 degrees for when omega is less than what? Well, let's actually fill this out a little bit. So when we look at this whole part right here, we can see that our graph is going to be starting like this. Now, when we look at this part, we see that we have one slope. We only have one slope of 45 degrees, and it's a negative 45 degrees. So this is going to be down negative 45 degrees, and then it's going to go on to be 0 degrees. So we can say that in the answer, we have 0 degrees as long as omega is less than our 12.5, and then it's negative 45 degrees when it's along this slope right here. So it's negative 45 degrees when we have this 125, because it's the only thing acting on it, so 125 here. And then it's a negative 90 degrees, so it continues on being negative 90 degrees after this 1,250. So we can write 1,250 here. Now we're going to tackle the first part. This WC is going to be equal to this part right here. And we know that this is 125. So our WC is equal to 125. And then our AWB at 1 rad per second is going to be the following. Let's look at this part down here. We have our AWB. And what this is going to be is this first part. So we're going to have a 20 log base 10, and then we're going to have our K naught. Well, we know that our K naught in this problem is 100 divided by 125. So all we got to do is plug this bad boy into a calculator. And this is going to give us approximately negative 1.94. So our answer is negative 1.94 dB, and that's how we would solve this problem.